Alright guys, welcome to this channel. So today I'm going to be showing you how to compute the MGF of a normal distribution. So for a continuous random variable, the MGF is given as expectation of e raised to power tx. Okay, so and remember from our expectation of x, that is integral of that x and the probability function, density function, as the PDF, right, and the x. So now for a normal distribution, we know that the PDF is 1 over sigma root of 2 pi exponential minus 1 over 2 x minus mu over sigma squared, ranging from minus infinity to infinity. Okay, now we are going to be using this exactly. So like here, moving to this part, so instead of writing this f, I'm going to write the whole of the PDF here, which I have here. Okay, so the MGF, which is still the expectation of e raised to power tx, will now be I just multiply this. I open the bracket with this square, and I have this one here, the x. Then I have MGF of this. Now I use my simple indices knowledge to use this one and this one together like this. So I have to get the LCM, which I did here. So if I set this over 1, okay, so that will be 2 sigma squared tx minus. Now I'm going to expand this one, then multiply with this minus, then that's going to give me all this one you can see here. Good. So to help me have something that I can really work with, this is portraying a quadratic formula, so a quadratic function. So I will just bring out the minus so I can really have what a quadratic formula looks like. Okay, so that's what I did here. I brought out the minus, and I have x squared and all of this. So we got from quadratic equation that we have ax squared plus bx plus c equals to 0. We all know this, right? And whenever we want to use the formula method, we use this. So I can transform the simple solution for a quadratic equation into this form by cross multiplying here, right? I cross multiply 2ax, then I brought this minus b to the other side, so I have plus b. I square both sides and I have square, and this square root is gone to this part. Okay, now I rearranged, then I have this, then I brought out 2a actually from this bracket, and which I have this one, then which led to this and this. So dividing all through by 4a, I will land here, because if I should divide 4a squared divided by 4a, but having a remaining, and this. So here is still the same thing as this. This is still the transformation into this. So, but this is actually what I actually need. I'm going to be putting this one into this formula. So this is my quadratic equation. This my coefficient is now my ABC. So this is 1. The coefficient of this one, which is b, is minus of the whole of this. Then the c is the mu square. So that's exactly what I would do here. So I still have my 1 over sigma root 2 pi equals to pi minus, then into the bracket of 1, which is my a here, then x plus minus b, x plus b, which is minus the whole of this one here, over 2 times 1, which is my a, and I squared everything. Just substitute and the whole of this, then you get to see yourself here. Okay, so if that is the case, then you bring out the 2 common here. Now there's a 2, there's 2 here and here, so I brought it out, I factorized it out so I could work with something I can cut. Now what happened here was that this square here onto this minus 2, that's 4. Okay, so I have 4 mu squared minus the 4, or when I square this minus 2, then the whole of this. That's why this 4 actually cancels this 4, and the 4 we're going to be having afterwards. So that's why I'm left with, after dividing this, I have this one. After dividing the 4 here, I have this one. This 4 is gone. Okay, then this 2 cancels this one. After I must have extracted these 2 and these 2 from this bracket, then I have this. Okay, then to this point. Okay, so I have not touched this part at all. I'm just dealing with this part of the equation. Okay, so moving on, I will now have this one. Okay, I still have this one. So I basically still continue what I was doing. Okay, so from where I stopped here, I opened this bracket. I opened this bracket. This bracket, I expanded it. This bracket, if I expand this, it's going to give me mu squared plus 2 sigma squared t plus mu raised to the power 4t squared, right? Then this minus is going to affect every other expansion that I have done here, which has led to this one. Okay, so of course mu square will cancel mu square, then I'll be left with just these guys here. Okay, so I have these guys here, and what I want to do is this minus have actually affects both this one and this one. So this minus comes to this one and this minus comes to this place. Okay, so if I should extract minus from the whole of these two, I'm going to, if I should extract minus, I'm going to be having minus 2 into the bracket mu mu squared t minus 1 over 2, because there's no 2 here, so I led me here and I still splitted it back using indices. Okay, so that's how this came about. And this one, we have this. Okay, so what I did was I brought this out and actually based my square root on both of these, since this one has square root and this one has square. I mean, so these two cancel this one and I'm left with this. So this is where the work is, which is we are almost done. So I extracted all of this as being a constant because I'm working with the x. So I brought it out. Then I have the integral of all of this. So this one itself is actually looking like the PDF that we talked about earlier. So I would say, and you know, the integral of a PDF is equals to 1 from the property of PDF probability. Okay, so the summation of all probabilities is equals to 1. That's for district. So now I have this. The reason being that if I should consider this, in the aftermath of this one, I'll be making t to be 0. So I'll be having mu, just mu here. But if I don't want to make t to be 0 yet, and I still want to work with this, then I will say that this is my PDF for a normal distribution with the mean of mu plus sigma squared t and the standard deviation of sigma squared. So in that case, and I know this one, then I will substitute the whole of this guy with 1. I will be having this, and which led to this. Okay, thank you very much. Don't forget to like.